how to get this property. All right. Requirement. How to split the array into two subarrays such that A of I less than or equal to B of J. Yeah. Because I can be any element in A subarray, so we can choose the maximum of A subarray. B of J could be any element in the B subarray, so we can choose the minimum in the B subarray. Yeah. But these two subarrays, in general, not ordered. Yeah. All right. D.2, partitioning in Quicksort. Now we need to understand the detail, how to make that happen. Yeah. All right. Implement the device step. Yeah. We need to fix the implementation details. Yeah. Here, some technical problem you need to solve. Yeah. So this is an original array. Yeah. All right. When we do the split, yeah. So for the question like this, yeah, problem solving, yeah, when we start, we want to, the first time in our first try, we just want to find a solution. Yeah. May not be the best solution, but let us find one solution first. Okay? Yeah. So here, we do our first try. Yeah. When we start, yeah. The goal, we want to split A subarray, B subarray, and we do not have, here, we do not have the idea how large is A subarray, how large is B subarray. We don't know. Yeah. Yeah. Uncertain. So here, yeah. A lot of things uncertain in at this point. Yeah. All right. Yeah. How to make it certain? Yeah. So we want to, try to fix uncertainty in several places. Yeah. All right. Yeah. So the first thing is how to separate A subarray and a B subarray. We need some special element as a separator, right? Yeah. So here, there is one element. We need some special element playing the special role as a separator, separating two subarrays. Yeah. All right. The key property, yeah. And that special element should be in place. In place. Yeah. That special element is at its final right place after the whole array is sorted. In place. Yeah. Then we can use it as a separator. Okay? Yeah. Left-hand side of that separator, A subarray. Right-hand side of that separator, B subarray. Yeah. All right. But still, some uncertainty here. How can you find an element that is in place? That's hard, right? How to figure out some special element that is in place? Another technical problem we need to solve. All right. Determine the boundary of two subarrays. Yeah. Boundary. So that special element we treat as a boundary, yeah, of those two subarrays. Yeah. All right. Here you can see there is one special element between A subarray and B subarray. Yeah. Here we use the symbol P, yeah, representing some special concept called a pivot concept. Yeah. All right. So this element, we call it, it's a pivot element. Yeah. We use it as the separator between two subarrays, And we require this pivot element must be in place. Yeah. Then all the values of A subarray must be less than or equal to this P value, and all the values of B subarray must be greater or equal to the P value. In that way, that A subarray, B subarray, after they are sorted, you put them together, automatically ordered, right? Yeah. No further work. After you conquer A subarray, B subarray, you put them together, because when you start, you already have this condition, right? Yeah. When you do the partitioning, you make this condition happen. Yeah. Then, in the combined step, you enjoy the result. You put them together, automatically ordered. Yeah, that's the idea. But you need to solve a few technical questions. How to find this pivot element, right? Yeah. That's hard. Yeah. If you can solve that technical problem, then you can complete that partitioning step. Yeah. All right. Which element is used as the pivot? First, we need to answer this question. Yeah, pivot. Yeah. We need that pivot element, but which one? Yeah. One of the elements in a given array should be used as the pivot, but which one? Right. That question. Yeah. Because we do not have any information from the given array, right? We do not have any information. Yeah. It's unknown. Yeah. If the data in a given array is unknown, then any element has an equal role in the array, an equal chance. Yeah. No, there is no special information. So which element has better chance to be the pivot? No, all elements have the equal chance to be the pivot. Yeah. So in this case, then it's a random selection, right? It's a random selection. Yeah. Because you pick the first element, last element, element in the middle, anywhere in this array, then they have an equal chance to be a good pivot. Yeah. So it's a random selection question. Yeah. No reason to favor any particular element. Yeah. So when you look at this sentence, no reason to favor any particular element in the sense of values. Yeah. Here, when we say this sentence, we mean in the sense of values. So value-wise, no reason to favor anyone. Yeah. Value. Yeah. We know, based on our intuition, if we know which element is the median, then median is the best pivot, right? Yeah? Yeah. Based on our intuition, median in the middle. So then it can split all the other elements evenly, right? Yeah. Evenly, then based on our balancing principle, that's the best split. Best split. Yeah. Split evenly. Yeah. Right. But you don't know which one is the median, right? Yeah. And you don't want to find the median. No. Too much work. If you find a median, too much work. Not worth it. Yeah. Not worth it. Yeah. Yeah. So you cannot choose the median as the pivot. Yeah. In this step. Right. So it's a random selection. Yeah. Random selection, you don't need to do anything, just random select one. Then that's the pivot. Okay, all right. Yeah. But although regarding the values, you do random selection, but there is another factor you need to consider when you work on this pivot element. Position factor. Yeah? Position factor. Yeah. In a given array, all those elements, they have different positions. Yeah. Positions are different. Yeah. Although the values we do not know, yeah, so we just random select anyone. But the positions in that array quite different. The first position, second, third, last, so many different positions. Some positions are convenient, but some positions are not convenient. So we need to also try to find some convenient position for the pivot. Yeah. In this step, it's not random. Yeah. Because the positions, the roles of those positions are quite different. Yeah. So we need to study that position factor here. All right. Yeah. Let us use a simple diagram to look at the difference using different positions for the pivot element. All right. If we randomly select one position somewhere in the middle, yeah, and use this position for the pivot, yeah, then you can see when you try to put some elements less than or equal to this one to the left-hand side, some to the right-hand side, yeah, but when you select this one, you do not know this position is the final location for this element. You don't know. It may not be in place, right? In general, it's not in place. If it's not in place, you need to move it, right? Yeah. But when you move, you need to also change the elements in other places, right? Yeah, other places. Then you need to do a lot of work. You need to do a lot of work. Yeah. So based on our intuition, in this step, yeah, this position not very convenient. Yeah. Because when we move elements around this position, yeah, we need to, some elements in A subarray, some elements in B subarray. So we need to move elements around this position, then its role just like a roadblock. Yeah, because you need to do a lot of work, you know. Yeah, it's a roadblock when you move elements around, left to right, right to left. It's a roadblock, okay? Yeah, so it's not convenient. Right. So we want to avoid the roadblock positions. We want to avoid roadblock positions, okay? So we want to pick the special positions, and they will not be roadblocks. Yeah, not a roadblock. They do not block anything. When you move elements around, those special positions, they do not block anything. Okay? Yeah? Yeah. So the special position, you can see, yeah, from this diagram, you can see the first position in the array or the last position in the array. Yeah? You don't need to touch them, right? When you move other elements, yeah, first one or the last one, you don't need to touch them. Yeah. So you move around without any block. Okay? So you can move elements easily. Yeah. Yeah. So you do not need to worry about first element or the last element. Yeah. You never touch them. Yeah. So then you can arrange other elements following the given criteria. Yeah. The criteria we like to have here. Move other elements using these two inequalities. Yeah. So now you fix that position factor. Yeah. Position factor, yeah. First one or last one. Put your pivot element there. Yeah. All right. Yeah. Yeah, so position-wise, yeah, there is a difference. Yeah. Here, let us use the last position as the to hold the pivot element. Okay? Yeah. Although some implementation use the first position. Yeah. No difference. Yeah. Same idea. Yeah. All right. Then, next, we need to split. A subarray, B subarray, we need to figure out. Yeah. What are those elements that belong to A subarray? What are those elements that belong to the B subarray? Yeah. All right. Yeah. All right. Yeah. So the elements in A subarray should be less than or equal to P value. Elements in B subarray should be greater or equal to P value. Yeah. Yeah. Although greater or equal, but yeah, in order to make it certain, so we can remove this equal case. Yeah, because all equal case we put in A subarray. Yeah. Yeah. Otherwise, both equal, so then, you need to determine. Yeah, for the equal case, do you want to put in A subarray or B subarray, right? Yeah, yeah, yeah. All right. Then, D.3, implementation in partitioning. So now we want to, see the picture. We want to see how things work. So based on our ideas, yeah, how to make it work. Yeah, all the details. All right. Straightforward implementation. Now, I said that first try, we just find a solution. It may not be the best solution. We just find one first. After that, we improve that solution, because that may not be. It's a lot of problems. We need to fix those problems. Yeah. All right. So when we start our first try, we use two auxiliary arrays to hold A subarray, B subarray. Use auxiliary arrays. Yeah. When we use auxiliary arrays, then much easier. Yeah. For data manipulation, much easier. Yeah. Here we don't worry about the extra space used in the auxiliary array. Yeah. All right. Yeah. So we scan the array from beginning to end, from left to right. We scan once. We want to find A subarray and B subarray after one scanning. All right. Yeah. But there are, here, this time, we use two auxiliary arrays. Yeah. All right. So here, two extra arrays. All right. Yeah. Then, it's easy. The first element, when you start with the first element, you compare it with P. If it is less than or equal to P, then you drop into the first auxiliary array. If you see the value is greater than P, then you drop it into the second subarray in order, okay? Yeah, in the natural order. Yeah. Drop one by one, okay? Yeah. After one scanning, you get a whole A subarray and a whole B subarray. You complete the partitioning. Yeah. All right. Yeah. So this first try, very easy. Very easy. Yeah. Yeah. All right. But there is a problem. Yeah. The solution, definitely not the best solution. Yeah. The reason is we need to use two auxiliary array. That's the extra space we need to use. Extra space we need to use. Space, location, that's the resource. That's the memory resource. The more memory resource you use, the overall performance will be slower, because your memory resource is limited. Is limited. Yeah. If you use too much resource, more than necessary, you slow down your overall performance. That's the problem. Yeah. All right. So in our algorithm design, there are two factors we need to consider. The first factor, the primary factor is the efficiency, the number of operations. Yeah, that number. We use that to measure efficiency. But that's the primary factor. Primary factor. That's the number of operations. Or you call them basic operations. Yeah. But there is a secondary factor. Not as important as the primary, but also important. Amount of space used. Yeah. Even with the same number of operations, then you want to use the minimum amount of space. Yeah. The secondary factor consideration. Yeah. All right. Here, we want to save the space used by those two auxiliary arrays. We want to eliminate those two auxiliary arrays. So can we use the space in the original array to do the data manipulation? Yeah? If we can manipulate elements within the given array, then we don't need to use auxiliary arrays. We can save a lot of space. So that's our next technical problem we need to solve. All right. Yeah, because that after that, and then you can copy back to the original. But you use that auxiliary array. So you use extra memory space. Yeah. So that's not the best way. Right? Yeah. So the next step, we need to eliminate these two auxiliary arrays. Yeah. All right. So how to eliminate? Yeah, that question. Yeah. All right. Yeah. Here, yeah, there is a, basic consideration in algorithm design. Yeah. Yeah. Control extra space used. Extra space. Huh? So what do you mean extra space? Yeah. Yeah. Because when you work on a typical problem, yeah, in algorithms, typical problem, you need to store input and output, right? Yeah. Input and output we treat as the normal space because for all problems you need to store input and output. You need to use certain amount of space. That part you cannot save. You have to use that much. Yeah. But the space other than input and output, then we call extra space. The extra part, then you can try your best to save extra space. Yeah. And here, these two auxiliary, that's the extra space we used. Yeah. All right. So here, we want to minimize extra space used when we do partitioning. Yeah. All right. Yeah, so here, let me describe this idea. Very simple. Yeah. All right. So we divide all the elements other than pivot element into different regions. Yeah. The first one, we call it S region. Yeah. Smaller or equal to P value. Yeah. So we're putting S region. L region larger than P value. So we're putting L region. Okay. All right. Then the third part, U region, we mean unprocessed element. Yeah, because some elements we haven't done comparisons. So U region, unprocessed region. Yeah. when we do scan, we just control. We manage these three different regions for different types of elements. Yeah. All right. Yeah. So at the beginning, when we start for A array, yeah, all the elements in A array, we put in S region. At the beginning, it's empty. Yeah. B region, B array, L region, at the beginning, they are initially empty. Yeah. Then we grow. Yeah. When we add elements into those regions, so we grow those two regions. Yeah. All right. Then unprocessed elements at the beginning, yeah, whole except the P. Yeah. Other than P, all the elements are in the unprocessed region. Then at the end, it becomes empty. So we process all the elements. Yeah. So we will manage these three regions to complete one partition step. Yeah. All right. Yeah. Next, I want to use a concrete example to show you the partition details. Yeah. So you see, yeah, when we do comparisons, yeah, and do data manipulation, yeah, swap here, there, yeah. So let you see the whole picture through this simple example. Yeah. All right. Concrete example. Yeah, I use this simple short array to, describe the partition details. All right. When we start, we select the last element as the pivot. Yeah, here, this 4. So we use different colors, yeah, for different types of elements. Yeah. All right. At the beginning, yeah, all these white color elements, they are in the U region. Yeah. All right. Then we use extra space to do the swap operation. We need to copy elements. Yeah. But we only use one extra space. That's enough when we do swap operation. Yeah. All right. Yeah. Then let's run step by step. One scanning from left to right. All right. When we start, S region empty, L region empty. All right. First comparison, compare 2 and 4. Pivot. 2, the first element less than the 4, yeah, it should go to S region. Yeah. So we drop it into the S region. Yeah. Second comparison, 8 and 4, 8 greater than 4. 8 should go to the L region. Yeah. Yeah. So here we use different colors. S region we use yellow color. L region we use green color. Yeah. Third comparison, compare 7 and 4, greater than 4. So 7 should go to the L region. Yeah. Yeah. So no problem. Yeah. One by one. Yeah. All right. The next comparison number 4, compare 1 and 4, element 1 less than 4. So 1 should go to the S region. So we color 1 yellow. Yeah. But after that, you see yeah, something not quite desirable, because your green region separate yellow region, 2 parts of the yellow region. So that's not good. Because we want yellow region, all the elements in yellow region take consecutive locations. Yeah. And all the elements in green region also occupy consecutive locations. They're more convenient, okay, as a whole block. Okay. Yeah. But here we need to do some work. Yeah. We need to make element 2 and element 1 adjacent. Yeah. So we need to do some work before next comparison. Yeah. Think about what is the easiest operation to make element 2 and element 1 adjacent. As easy as possible. We don't want to do too much work. Yeah. Simple work to make element 2 and 1 adjacent. Yeah. The simplest operation, swap these two elements, right? Swap. Element 8 and element 1 do swap operation. Use this extra space, we can do swap operation, right? Yeah, copy 8 to temporary location, and copy 1 to that older location occupied by element 8, then copy that swap location element back. Yeah. All right. So now, next step, we swap element A and 1. Okay? Yeah. After that swap operation, now you can see, yeah, all the elements in the S region, they occupy consecutive locations. Yeah. Now, it's great. Okay? All right. Then after that, we can do next comparison, number 5, 3 less than 4. So 3 elements should be in yellow color, but we need to do another swap, right? Swap element 7 and element 3. Okay? After that swap, then, yeah, so we put all elements in S region or L region, you know, in consecutive locations. Yeah. All right. Comparison number 6. 5 greater than 4, so it should be in L region and no swap. Yeah. Yeah. No swap. Right? All right. Then, after the last step, yeah, because remember the pivot element, the last step we need to put it in place. The pivot element must be in place. Okay? Yeah. So another swap. Yeah. Another swap, you can put it in place. Swap between element 8 and element 4. After that, you put the pivot in place. And you get an A subarray, you get a B subarray, and the amount of space you used, only 1 extra space. You do not use auxiliary arrays. So you save a lot of space usage. Yeah. All right. Here, there is a special concept at this point I want to say. Yeah. Because here, the extra space you used, only 1 location you use as an extra space. So we look at the extra space you used. If the extra space you use is in big theta of 1, that means constant number of extra space. Big theta of 1, bounded by certain constant. If your algorithm has that property, we have a name for this algorithm. We call it in-place algorithm. Okay? Yeah, in place. This word. In-place algorithm. Yeah. But be careful. When you use this in-place term, we have 2 different meanings. One is the element in place. Another is algorithm in place. Okay? The meaning is different. Yeah. Most of you can understand the elements in place easily. Yeah, but for the algorithm, if it is in place, that's the meaning. The actual space used is in big theta of 1. Then we call this algorithm is in-place algorithm. Okay? All right. Yeah. If I use example, one example for in-place algorithm, insertion sort. Insertion sort is in place. You just use 1 extra space, you do insertion, right? You lift, you copy, current element, then you do shift, then you copy back. So extra space used, 1 extra space location, insertion sort. Yeah. But quicksort, this step, then you should be careful. Quicksort, although when you look at the partition step, you only use 1 extra space. It looks like in place, right? But there is a problem. So if you compare quicksort and quicksort, here we compare quicksort and insertion sort. One is insertion sort. One is quicksort. Yeah. if you look at each step, insertion step, and each partition step, both in place, right? Extra space of 1. But there is a key difference. This quicksort, you use recursion. Insertion sort, you use iteration, right? You do not use recursion. Yeah, you use iteration. You do not use recursion. Then, remember, at the beginning of our module 3, I talk about recursive algorithm. There is a big problem. When we run recursions, we need a stack, right? There is some deep memory stack used. When you need to use the memory space to hold that stack of data, do you treat as extra space, right? Extra space. But that extra space is not under control, right? It could be very large. So for that reason, yeah, quicksort, insertion sort, we treat them differently. Insertion sort we can call in-place sort, in-place algorithm, in-place sort. Yeah, because absolutely no large extra space used. But quicksort we cannot because of that stack. The deep stack could be out of control, so we cannot call real in-place sort. Yeah, that's the difference. Yeah, all right. All right, next. Yeah, yeah. How to control S region, L region? Yeah. So I just described the basic idea, but technically, when you write a program, you need to, work on your variables carefully, right? Yeah. So here, one small technical question you need to answer: how to control S region and L region? Yeah, actually, pretty easy. Yeah. Oh, sorry. Yeah. We use two indices. Yeah. I, J, we can control S region and L region. Yeah. I index, J index. S region, we use the location original A array from index 0 through I. Yeah. L region, location from I plus 1 through J. Yeah. Every time when we increase, we grow S region, we increment I index. Every time we increment L region, we increment J index. Yeah. So we can manage those two regions easily, right? Yeah. Yeah. Grow S region, grow L region. Yeah. When we do swap, yeah, so you can maintain both regions gracefully. Yeah. All right. Yeah. All right. Then we have two cases we need to study: worst case and the best case. Worst case efficiency and the best case efficiency. Worst case, relatively easy to see. Yeah. So let's look at the worst case first. Then the best case. Yeah. Yeah. So we have a good chance we can complete Part D today. Yeah. Last two cases. For the worst case, then recall our understanding. Now, when we split the data, when we split, divide, conquer, so in the divide step, if we split the data right in the middle, then we avoid the worst case, right? Yeah. If we split data in the most unbalanced way, extremal type, yeah, 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 most unbalanced way, then it corresponds to the worst case. Yeah. All right. The best case, split evenly. That's the best case. Split in that extremal way. Yeah. Then worst case. Yeah. All right. extremely unbalanced. If the partition is like that, then partition A subarray, B subarray, how about your A subarray is empty? And other than the pivot, all elements are in the B subarray. Then the most unbalanced split. Yeah. If you always have that kind of split, that's the worst case. Yeah. All right. So here, using this diagram, yeah. So the split, all in yellow color, other than P, all in yellow colors, right? That's an unbalanced split. Yeah. All right. All in S regions, other than P. Yeah. Yeah. But another one, other than P, all in L region. Yeah. So another unbalanced split. Okay? Yeah. So if in every partition step you have this kind of unbalanced split, then at the end you get the worst case. Yeah. All right? Yeah. All right. And you can see the number of comparisons we need very easy, because each partition you need to do n-1 comparisons. Okay. After n-1 comparisons, you reduce the problem size by 1. Yeah, because the P is in place. You put a P in place. Other than P, the remaining n-1 elements, you need to apply partition another time. But the size is only 1 less than the original size. Yeah, so that's not efficient. Every time you reduce the problem size by 1. Yeah. So, yeah. So that's the worst case. Yeah. All right? Yeah. So here, I also ask you which one. Yeah, because if you compare which case is worse, because if you only look at the comparison part, they are the same, but there is small difference. Swap part. For example, this case, you don't need to swap, right? P already in place. But this one, you need to swap. You need one more swap. Okay? So that is slightly worse than the previous case. Yeah. All right. All right. So that recurrence condition for the worst case. Yeah? Because when we look at the complexity function, the number of comparisons, this T, we represent the number of comparisons. Yeah. Every time after n-1 comparisons, you only reduce the problem by size 1. So this is your recurrence relation. Yeah. When you calculate this one, you do recursion, every time reduce by 1. Then at the end, you add up all these numbers, yeah, from 1 through n-1. That is this number. This number, you can see it's in big theta of n squared. That's the poor worst case, right? Yeah, n squared. Yeah, that's very bad. Yeah, that's the bottleneck. Yeah. So for the quicksort, you cannot avoid the bottleneck. Yeah, the poor worst case. Yeah. All right. All right. So now example for worst case. Yeah, because we have these two different examples. Here I just run some special examples. Yeah. Do partition. Here I need to do many partitions. I show you for each partition, it looks like. Yeah. Yeah. Yeah, it's easy to see. Yeah. Every time you reduce the problem size by 1. Okay? Yeah. All right. But the best case, you need to do a little more work. Yeah. Because for the best case, you do even most balanced split. Yeah. All right. Yeah, study best case. Most balanced partitioning. Yeah. Each step. Yeah. The size of S region, L region, almost the same. Yeah. In that case, we use this recurrence relation. Yeah. All right. The base case. Yeah. Then recurrence relation. Yeah. The conquer, because each subproblem approximately half the problem size, n over 2. But we need to conquer 2 subarrays. So we have 2 times T of n over 2. Then the partitioning step, we need n, big theta of n, yeah, n comparison. Let's say n comparisons, approximately n comparisons. Okay, yeah. So now we need to calculate T function from this recurrence relation. Yeah. But this one, you can see, yeah, if you compare it with the merge sort, you can see in the merge sort we have almost the same relationship, right? Because the merge step, this step is n minus 1 comparisons. Then we simplify it, we replace it by n. Yeah, that's merge. So here, you know, almost the same. Yeah. And for the merge sort, I delay that. Yeah. I said, because in the quicksort, we will solve the same problem. So I just want to do it once. Yeah. So merge sort and quicksort, yeah. I just do it here. Yeah. I show you one special way to estimate here. Estimate this T function. Yeah. So we use a special method we call the recursion tree method. We construct recursion tree to estimate this T function. We draw a binary tree, yeah, you know, showing the recurrence information in the binary tree. Yeah. Then we do the estimate. Yeah. So all right. But when we build this recursion tree, we need to know how many levels do we have in this tree. So we use this inequality to help us estimate the number of levels. Okay? Yeah. You know, this k levels. All right? Yeah. We do recurrence relation this k times. Yeah. All right. Yeah. All right. Because after we yeah. Right. Recurrence relation 1. Yeah. 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 Because after the problem size between 1/2 and 1, then we reach the end. Yeah. We reach the, you know, the bottom level. Yeah. We can stop recursion. Yeah. Then in each level, in our recursion tree, each level, we collect. Yeah. So here, this big theta of n, because this big theta is an asymptotic notation. It's not convenient in calculation. So when we do calculation, we want to remove this big theta notation. So we replace it by constant c times n. Okay. C is some constant c, constant number. All right. So then in each level, we put in a node only the non-recursive term. Yeah. So Cn, that's the non-recursive term. Yeah. And the T part, because we need to split. In every level, we need to split. One node we split to 2. 2 nodes we split to 4. 4 nodes to 8, and so on. Yeah. Split, yeah, to the bottom. Okay. All right. Then at the end, we need to accumulate non-recursive terms. Accumulate. All the non-recursion terms. Yeah. Because the recursion terms, when we reach the bottom, T of 1 equals 0. So the T part, when we hit the bottom, 0. It's gone. So we only need to accumulate the non-recursion terms, Cn. All right. So each level, the total, you add up, total non-recursive Cn. Okay? This 4, you're adding together 4, you also get a Cn. So each level, the same Cn you get. Okay? All right. How many levels do we have? K level, K equals log base of n. Yeah. So K times Cn. Yeah. So what do you have? Yeah. Because K, you can use log n to estimate. Yeah. So what do you have is the total cost big theta of n log n. Yeah. And that's the best case. That's the most balanced partitioning. Yeah. So for the best case, you get n log n. Okay. If you compare insertion sort, yeah, so why insertion sort is so special? Insertion sort, yeah, sort. The best case, big theta of n. Okay? Yeah. Merge sort, quick sort, both their best case in big theta of n log n. Okay? Yeah? Yeah. Yeah. So now you can see insertion sort is very special for the best case. Yeah. All right? Yeah. Yeah. So now, after this, that's the average case efficiency. Here, regarding average case efficiency, it's very hard to do analysis on average case efficiency. Yeah, because it's so complicated. If we consider the average case, we need to estimate average of all the cases. That's too complicated. Yeah, it's hard to do analysis on average case efficiency. Yeah. Then, how people compare average case efficiency. Yeah. So here, mainly people use the experiments, write the programs, run, compare different sorts, merge sort, quick sort, insertion sort, and many other sorts, apply them on random data many times. Yeah. So, yeah. Many times. Then take the average. Yeah. People can only use experiments to compare their average case efficiency. Yeah. Because their average case efficiency so not a insertion sort. Insertion sort in big theta of n squared. So the merge sort, quick sort, if you use asymptotic notation, their average case efficiency all in big theta of n log n. Then you cannot see the difference. Which one is better, which one, no. You cannot see it from the asymptotic notation. To see the difference, you can only do experiments. Yeah. Yeah. So after people run experiments on, random data many times, and then take the average. Yeah. So this quick sort is the best. Yeah. So then we can say quick sort has the best overall efficiency. Yeah. Merge sort, not the best. Yeah. Not as good as the quick sort. Yeah. All right, yeah? Yeah. All right, yeah, because sometimes the students ask me, because I may give you a question, which algorithm has the best overall efficiency? Yeah? In my quiz or homework, or test, I may give you a question like that. So I give you multiple choice, give you 4 different sorts. Ask you, which one has the best? Then student asks me, how do we see quicksort has the best case efficiency? Yeah, if we just look at from the asymptotic notation, we cannot see. Yeah, so then I explain. So people run the experiments to see the difference. Yeah, that's the answer. Yeah. using experiments. Yeah. Because they are in the same category. Yeah. Same category. Yeah. All right. Yeah. So we finish part D and this module 4. So on Wednesday, I will start a new module, module 5, heap sort. Yeah. Heap sort, the title of module 5 is advanced data structure. I want to address the data structure part in module 5. Yeah. So advanced data structure. Yeah. So that's another interesting problem. Yeah, interesting. Yeah, we look at from the data structure point of view. Yeah, the data structure quite special. Yeah. All right. So then. All right. Yeah. Yeah. So.
We still have one more slide.
Yeah. One more slide. Yeah. Let me see. Anything important? Yeah. Oh, improve. Oh, yeah. I talk about randomization. Yeah. Yes. Yeah. Randomization technique. Yeah. So that's also something related to experiments. Yeah. Because. Yeah. So here, let me just say quick comments about this randomization technique. Yeah. Because when you select so here, if given array, if you just use the given last element as the pivot, that's called a no randomization. If you do randomization, you select anyone in the middle as the pivot. You do swap, one swap. Yeah, that's the randomization. Yeah. Then when you compare these two, yeah, on random data, you can see the difference is minimal. Yeah. I remember I assigned the project once to my students several years ago when they do comparison. And finally, the randomization way actually slightly slower than the normal way. Yeah. Yeah. The reason you need to do extra work, one swap. Okay. But after you do one swap, the random data, and randomly, because data is generated randomly. Okay, so no difference. So every time you do one more step, so at the end, you do slightly worse. Yeah. But this randomization step has some value, because if the data is given in ascending order or descending order, the data could be in ascending order or descending order. If you still use the last element or first element as the pivot, then you get the worst case. But when you do randomization, you can break the pattern, because you select somewhere in the middle. Okay, yeah, then it is better. Yeah, yeah. So that's the yeah. Although there are some other method, median of 3 method. Yeah, median of 3 even slower. Yeah. Ask my student did experiment, because you need to do more work. Every time you select 3 elements, then you find a median. Then you use that median as the pivot. You do more work. Okay? Yeah, at the end. So it's worse than other methods. Yeah. So then we just use the normal quicksort. Yeah. But if you know your data has good chance to have ascending order, descending order, then you should do randomization. Yeah. All right. Yeah. So let me stop right here. Yeah. 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 Just some comments. Yeah. All right. Yeah. So so we finish this part and also this module. So next time we start module 5.